The Sun, the largest mass in our solar system. Containing as much mass as 333,000 Earths, the Sun contains 99.8% of the mass of our solar system. It's made up of hydrogen and helium gas. Hydrogen particles make up the majority of the mass and number of atoms in the Sun. Helium makes up the second largest portion, and all other elements make up less than 2% of the mass and about 0.1% of the number of atoms. So, the Sun's a pretty big deal for us. But compared to other stars in the universe, our Sun's pretty unextraordinary. Our Sun is not the coolest, smallest, or darkest star, nor is it the hottest, brightest, or biggest. As you can see by these various superstars. This blue superstar right here is named Eta Carinae. It's 100 times more massive than our Sun and is relatively close to the end of its life. This peach-colored superstar, named Betelgeuse, is 300 times larger than Eta Carinae, and if it was in the place of our star, it would reach all the way to Jupiter. And this is the largest known star in our galaxy, VY Canis Majoris. So back to our star. How does gravity on the Sun work? The first step to understanding gravity on the Sun is to understand gravitational contraction. Gravitational contraction is defined as the collapse of gas and dust to form stars, planets, and other objects under gravitational attraction. This process releases potential energy as the mass becomes closely packed together. This process gives the star energy and powers the early protostar into what we define as a star. But there's more than one type of gravitational force acting on stars. After gravitational contraction, gravitational equilibrium occurs. This force is what holds the Sun together. Now the star is officially defined as a star, but in order to be stable it must achieve gravitational equilibrium. For this to happen, nuclear fusion must occur. We'll talk about nuclear fusion a little later. All you need to know for now is that it creates energy that helps maintain the high temperatures of a star and creates pressure to push outwards on the force of gravity. This picture helps illustrate this point, as you can see the gravitational force in green and the pressure caused by nuclear fusion in red. Now that we understand how the Sun is held together, we can talk about the layers of the Sun. First, though, we need to talk about solar wind. Solar wind can be defined as an outward flow of particles, mostly electrons and protons, from the Sun. These particles are expelled because of the chemical reactions occurring in the Sun. This metaphorical wind causes the aurora when it hits Earth. Next, we have the corona. This is the Sun's outer atmosphere. The corona is an incredibly hot layer of the Sun. The density of this region, however, is very low. It is also very dim in comparison to the other layers of the Sun. The chromosphere comes next. The chromosphere is the layer of the solar atmosphere in between the corona and the photosphere. The chromosphere is a dim layer of less dense stellar gas. The chromosphere is only visible during an eclipse. Otherwise, we can't see this layer. The layer that we do see is the photosphere. It is the innermost layer of the three layers that comprise the Sun's atmosphere. The photosphere is not really a surface in how we would normally define it. This layer is just how far we can see into the Sun. The chromosphere and the corona are transparent and visible light, but not the photosphere. Thus, this is the layer we can see. Moving into the interior of the Sun now is the convection zone. This is the layer where energy is transported outwards by means of convection. Hot gas travels up through this zone, and then it radiates photons into space, which are then perceived as sunlight, seen through the photosphere. Once the photons are released, the gases cool off and settle back into the Sun. The next portion is the radiation zone. This is the portion of the star where energy is transported outward by the movement of photons through a gas from a very hot location to a cooler one. This is a much hotter and denser region of the star. And finally, the core. The core is the central portion of the Sun's radius where hydrogen is fused into helium. This nuclear fusion releases the energy that enables the Sun to shine. It is an extremely dense region, but it is still completely comprised of gas. So we've mentioned nuclear fusion, but now we're going to explain in depth what it actually is. There are two kinds of nuclear reactions. The first is nuclear fission. Nuclear fission is when a single large nucleus splits off into two smaller nuclei. In comparison, there's nuclear fusion. This is when two smaller nuclei form to make one large nucleus. This is the kind that we're going to be discussing in relation to the Sun and stars. Nuclear fusion is able to occur in the Sun due to the incredibly high temperatures. Without that, it wouldn't be able to happen. The high temperatures enable the nuclei to propel towards one another at high speeds and bind together. In this diagram, we see the basic nuclear fusion process. We see 4 hydrogens bonding together to form one helium atom while releasing energy. While this is a relatively simple process, taking a closer look at the fusion may seem daunting. But remember, it's pretty simple at the core. The first step of hydrogen fusion includes 2 protons fusing to make one nucleus. This step occurs twice in the overall reaction to produce the appropriate amount of atoms needed to form a helium atom. Next, the newly made nuclei fuse again to another proton to make 2 nuclei of helium-3. This step also occurs twice in the overall reaction. And finally, step 3, the 2 helium-3 nuclei come together and form a helium-4 atom. This releases 2 excess protons in the process. At the basis, this process is just how hydrogen fuses into helium in the Sun to create energy. Once these particles are created, though, how does the energy escape? The energy gradually leaks out of the radiation zone in the form of randomly bounding photons. The photons bounce off fast-moving electrons and bounce around until finally making it to the surface of the photosphere, where hot gas reaches the surface. So we've discussed all these properties of the Sun, but how do we know all of this? Astronomers investigate these things in one of 3 ways. The first way is through mathematical models. From the Sun's mass and composition, astronomers can determine the Sun's radius, temperature, luminosity, and age. The second way is through sunquakes. In a similar way, we can learn about the Earth's composition through earthquakes and seismology. We can learn about the Sun from patterns of vibrations through helioseismology. And the third way in which astronomers can learn about the Sun is through tiny particles called sun neutrinos that escape from the Sun. By observing these particles, we can tell what's happening in the core. Now that we've talked about our Sun and the nuclear fusion that occurs with it, we can talk about how to classify stars in our universe. First, we need to define 2 terms that are incredibly important in classifying stars. The first is luminosity. Luminosity is the total energy emitted per second, or the amount of power a star radiates. This is measured in energy per second. The next term is apparent brightness. This term is the amount of starlight that reaches the Earth, and this is measured in energy per second per square meter. This picture illustrates these 2 terms well, and we can get these 2 numbers through these equations. Apparent brightness of a star depends on luminosity and the distance, and we can determine a star's luminosity if we can measure its distance and apparent brightness. The distance is measured using parallax, and it's important for both equations. So now that we've defined these 2 terms, we can move on to the laws of thermal radiation. The laws of thermal radiation help us to determine how hot stars are. The first law states that hotter objects emit more light at all wavelengths. The second law states that less hot objects emit light at shorter wavelengths. What these laws basically tell us is that by measuring the spectrum of a star, we can get its temperature. That's what this next slide can show us, a star spectrum of light. The stellar spectra is defined as the classification of stars based on spectral characteristics, with the hottest stars being listed at the top and the coolest stars at the bottom. And once we have the star's temperature, it can help us to classify it. Stars often aren't alone, however. About half of all known stars are in binary systems. A binary star system is 2 stars orbiting each other. They're gravitationally bound. Here listed are the 3 distinct types of binary star systems. The first is visual binary. These stars we can directly observe with telescopes, their motions around one another. The next is eclipsing binary star systems. This system has an inclination of the orbit of basically 0, meaning that it causes eclipses of one another. The eclipses of these stars are what tells us that there are 2 stars present. The final type of binary star systems is a spectroscopic binary. The star system is seen as one object because of the large distance. However, by using spectroscopy, we can see that one star approaches while the other recedes, telling us that there are 2 stars present. So now that we have discussed all of these components of stars, how do we classify them? The answer is fairly simple, by mass and lifetime. High-mass stars have high luminosity, short lifespans, large radiuses, and appear to be blue. Low-mass stars, in contrast, have low luminosity, long lifespans, small radius, and appear to be red. By looking at our Sun, we can classify it as a low-mass star. Stars can vary greatly in mass. The mass of stars can run from 0.0 times the mass of the Sun all the way up to 150 times that of the Sun. Objects less massive than 0.08 times of the Sun are known as brown dwarfs. However, masses are only known for stars that form binary systems, with about half of all stars being in those systems. This means that there are no solo stars out there whose mass we have not calculated. The Hertzsprung-Russell diagram is pictured here. This diagram plots the luminosity as a function of the temperature of many different stars, with the luminosity on the y-axis and the temperature on the x. This diagram is important because it can tell us a lot about stars in one picture. Normal hydrogen-burning stars reside in the main sequence of the HR diagram, with mass increasing from lower right to upper left. Finally, in classifying stars, we can also classify star clusters. The first type of star cluster is the open cluster. This star cluster can contain several thousand stars and is found in the disk of the Milky Way. The second type of star cluster is the globular cluster. This star cluster can contain hundreds of thousands of stars all closely packed in together, and these clusters are mainly found in a halo around our galaxy. The Sun and the stars are truly some of the most incredible masses in our universe, and hopefully we've done a pretty good job of illustrating that for you. We hope you've enjoyed this presentation. Thank you for listening.